Okay, so today we're going to talk about lecture 4, which is an intro to ECS. And just a quick note on the upcoming lectures. So today we're describing what ECS is. We're going to talk about how we're going to implement the components and the entities in C++. So it's one thing to talk about the theory, it's another to actually give you the code that we're going to have in the assignments. And so we'll go over components and entities today, and a few slides at the end about the Vec2 class that we're going to be using throughout the term. Then in the next lecture, we're going to talk about the entity manager, and that's a class that we're going to use to actually manage the lifetime creation and deletion of the entities that we're talking about today. And once we have these two lectures in the bag, then we can talk about assignment 2 that will finally use these things that we've been talking about this week. So let me get started with the presentation here. Okay, so lecture number 4, again, we're actually getting into the ECS part of this class as well as talking about a Vec2 class. So what is ECS? Why do we want to use it? What benefits does it have? What drawbacks does it have? Etc. So why do we want to use ECS for games? So again, just as a reminder, ECS stands for Entities, Components, and Systems. So an entity is going to be basically any object in the game, whether it's visible or not visible. Anything that's in our game as a thing that's part of the game is going to be an entity. So for example, the player, so Mario or Mega Man or whatever running around in the stage, that's going to be an entity. A platform that the player might stand on or collide with, that's also an entity. A tile, a bullet, an enemy, a tree in the background, an invisible spawner that spawns things out of it. All of these things are going to be entities. So ECS is not strictly related to games. It happens to be particularly good for games because games are more dynamic than most pieces of software, right? We're not just editing things in a spreadsheet. Things are spawning, new things are coming in all the time, things are being killed and deleted, and so there's a lot of dynamic stuff going on that lends itself really well to ECS, as well as there can be a lot of different game mechanics that can be implemented with ECS that make it particularly good for games. But ECS does not relate only to games. It's a software design paradigm. But in order to really understand why we want to use ECS, I'm going to first take a look at object-oriented design. And so you've probably heard about object-oriented programming, right? So object-oriented programming typically involves you have classes and polymorphism, right? So that's the main thing about object-oriented programming, is that some objects can inherit from other objects. Object-oriented design is a kind of a level above that, where we are going to architect something around the fact that we have classes and polymorphism. And so object-oriented design talks about architecture, whereas object-oriented programming is the actual implementation of those things. I've completely made up all of that. It's not necessarily that's how it's going to be described everywhere, but that's how I want you to understand it. Some important notes first. Large AAA games can and have been made with object-oriented design for years, where instead of using entities and components, they just have an enemy class, then skeleton inherits from enemy. It's possible to do all these things. I would argue that that's a little bit outdated, and most people now are using some sort of compositional based design. But I've decided to teach ECS for this class because I think it is better for making games, and a lot of people in industry have that viewpoint as well. We won't be talking about it, but it also lends itself better for things like networking, etc., because our components are just pure data, which can easily be serialized, etc. But this will allow us to do many things quite easily, and also just because you probably haven't been taught compositional-based architecture for software before. Has anyone here had ECS in a course? I don't think we have it in anything else. So you may have used it. If you've used things like Unity, Unity uses something that is like ECS that we're going to be doing in this course. So some agree with ECS and some prefer object-oriented design. I cannot put a mathematical proof on the board that says which is better. But hopefully by the end of the course, if you don't prefer ECS, you will at least understand where it derives its power from and why I would consider teaching it for this course. So object-oriented programming or object-oriented design helps us manage data and code, right? It has a purpose, and it's really great in a lot of places in software architecture. And so when we're talking about object-oriented game programming, we would say, okay, an entity is any object in the game. And then when we talk about things like polymorphism or inheritance, we're thinking, what properties of things are shared between things? I'm sure you've all been taught we have a class vehicle, and car inherits from vehicle, but truck inherits from vehicle, and these things have their own little properties, but they all have 4 wheels or whatever, right? So that's what we're talking about here. So every entity in the game might have some sort of XY position. So maybe the base class entity would have an XY position, and then something like a tile, a player, those would inherit from that entity and then have their own properties, right? And then maybe a tile would have multiple types, etc. So what you would have is this sort of hierarchical decomposition of all the different types of things in your game. So up here, text is a little small, apologies, but up here we have an entity base class, and then maybe we have, okay, we're going to have some entities in the game that don't move, for example, right? So those would be static entities. We have some entities that move around, so those would be dynamic entities. So maybe a dynamic entity would have a velocity, whereas a static entity wouldn't have a velocity or something like that. Over here, static entities might be rocks or trees, etc. Dynamic enemies might be enemies or players. But down here, maybe now we have something that might be an evil tree. So what if we have a tree that inherited from static, but now there's an enemy that's also a tree? And so this is a completely cherry-picked derived example, but you see that this can lead to weird situations, right? And in the end, you might have like a derived class for every possible one of the 100 types of enemies you might want to have in your game, and it can get a little bit tangly. Not only that, but you have to decide on a hierarchy in advance, and if anything changes, now you have to go back and refactor tons of code and stuff. And so there are downsides to doing this for sure. I'm not saying it's 100% terrible, it's just there are downsides to doing that, especially when it comes to games, in my opinion. The entity component model, however, would be an entity is an object in the game, and then a component you can think of as a property that we would want to attach to an entity, right? It has this particular property. So for example, some basic ones could be a position or a speed or a velocity, right? So this entity is somewhere in the game world. So if we wanted to be somewhere in the world, we would give it a position. If we wanted to move around, we would give it a non-zero velocity. And just for a reminder, here I listed speed. I should change that to velocity. Speed means like the speed you are going, like the magnitude of the vector. Velocity would be your change in x and y. And so we're going to be using velocity in this course. You may want to have something called a bounding box. So a bounding box, that's the term for a little rectangular box that we put around something that we would want to interact with other things. So for example, maybe our player has a bounding box down here standing on the ground, and the ground would also have a bounding box, right? And if something didn't have a bounding box, then it wouldn't have collision. So maybe you have some type of gun, and it's a laser, and the laser can go through walls or something like that. So you wouldn't have maybe a bounding box on that. Also, you may want something to have health or not have health, right? So the player might have health. Does the tile have health? Maybe not in some games, maybe so in other games. If you want to be able to shoot a tile and have it take damage and then explode, you would give it some health maybe. Maybe you have a weapon on an entity or something like that. Or damage, like if this bullet has a damage component, if it collides with something else, then you know how much damage that thing it should take. So this is a compositional based design because we're going to have this big bag of tricks, this big bag of components, and we're going to be able to pick and choose which of these components we add to create a specific entity. So if we look back at that previous example, we would have all these different components down here. So for example, a position, maybe an AI component, a sprite. A sprite in this context is just like the texture that gets drawn to the screen. This says AABB, that's an axis-aligned bounding box, meaning it's just like, it's a rectangle that's not rotated. A velocity and an input. So let's say we have these different components, how can we build different things out of those? So for example, a tree, okay. Well, a tree, does it have a position? Yes, the tree is going to be somewhere in the game. Does it have an AI? Probably not. The tree just kind of stands there and does nothing. Does it have a sprite? Yes, because we actually want to draw the tree to the screen, and so we would give it some sort of texture or image that we want to draw. Would it have a bounding box? Maybe, if we want to be able to collide with it. In this case, they haven't given it a bounding box. Would it have a velocity? Well, you know, the tree kind of stays put. It's literally rooted in the ground. And maybe this input component, meaning that we could control it with the controller, that's not something we would attach to the tree. However, an enemy, let's say, you know, you're playing any game, anything that walks around and tries to kill you, it's going to have a position. It will be controlled by some sort of AI, no matter how basic or complex it is. It would have a sprite, it would have a bounding box, and it would have a velocity. And the player would differ from an enemy. Really, the only way the player differs from the enemy is that instead of being controlled by an AI, it's controlled by the player's input. And so we would have an input component on the player instead of an AI component on the player. But the really cool thing is that let's say we picked up some power-up that lets us mind control enemies. All we would have to do is attach an input component to the entity, and now we're controlling that as well, right? So it's really cool. We can give away or take away or give properties to these entities at any time. And so ECS uses composition-based design, compose, composition. That's where the root of that word comes from. So again, an entity is anything in the game. Components are properties that we attach to entities, and we've already talked about some of the things. One thing that we haven't talked about yet that I find really cool is like a gravity component. So if you attach a gravity component to something, now it is affected by gravity. So you could have a cool game where you have like a gravity gun, and whenever you shoot something, if it hits something, now that thing has gravity and like falls down, whereas before it was just floating in the air. And the important thing to note here is that if you go read about ECS programming, there are two big, I guess, overall flavors of ECS programming. One is where components have behaviors and functions attached to them. So the logic of the component and what it's supposed to do would actually be a function in the component class rather than in the systems. But for our case, the more sort of pure ECS, I'm not saying one is better than the other, but I happen to like this one personally, is where the components are literally just pure data. And like as base level data as you can get, like a few ints or something like that, or maybe a shape with a width and a height or something. So components are going to be pure data, and then the systems are the functions or code or logic that drives the behavior of everything, okay? So we might have a movement system, for example, a rendering system, a sound system, a physics system, etc. So let's have a look. Here's a couple more examples. We just talked about this. So let's say we have a 2D platforming game, like Super Mario or anything. So a player might have a position, a speed, a bounding box, a sprite, some health so they could take damage, gravity, and an input, right? So those are the components a player might have. An enemy, on the other hand, might have position, speed, bounding box, sprite, health, but maybe it's not affected by gravity. Maybe this is like one of those Lakitus in Mario where they just float through the air, but they would have some sort of AI behavior, right? So you could think of the AI behavior, you could say, how is an AI pure data, right? That doesn't make any sense. AI has logic to it. But what we're going to do is we're going to store in the AI component just data. So this might be an integer representing the type of behavior, right? And then in the system, we'll say, if the AI behavior is this, then carry out, maybe it follows the player. Or if the AI is runaway behavior, then it does this. So the logic is carried out in the systems, but we're keeping this to pure data. Now when we get to something like a bullet, maybe it would have a position, a speed, an angle, if it was shot at some sort of angle, a bounding box, a sprite. Maybe this, though, has a damage component, right? So we can think of, okay, if this thing with a damage component collides with something that has a health component, then we're going to subtract the damage from the health. Also, maybe it has something we're going to do in this, for our assignments, is a lifespan. So a lifespan is, let's say, for example, I'm playing a game and I shoot a bullet, but and the bullet is not like a hit scan bullet. It's actually, it's a projectile that moves at some speed. So in assignment 2, we're going to be shooting these bullets, and they're going to go off the screen if they miss something, right? But do I want it to just travel infinitely forever? So if I've shot 1,000 bullets, do I want all these bullets sort of living off the screen that I never see? No. So one of the things that I can do is attach a lifespan to it. So let's say I want a bullet to be shot, but I only want it to be around for 2 seconds, right? So if my game is operating at 60 frames per second, I could attach a lifespan of 120 frames, and then at every frame I can decrement from that counter. When it reaches 0, the thing automatically gets destroyed. So now I can attach these lifespans to things just by giving it that component, and the systems will handle all of that. And then something really simple like a tile might just have a position, a bounding box, and a sprite, because it doesn't do any of the other cool stuff. It just sort of sits there. But later on, if we did wanted to do something, like if maybe this tile turns into lava later on, we can just attach a damage component to it, and if the player stands on it, then they take damage, right? So we can make things, anything we want out of these components, rather than having to have everything thought up in advance. It's more of a dynamic, compositional-based architecture. And so just keep in mind that this is not the only way to implement ECS. When I talk about, especially when it comes to implementation, there are a million different ways to implement everything, right? So I'm going to show you the way that we're going to do it in our assignments, and just keep in mind that, as I said in the first lecture, this is a balance between efficiency, ease of use, and how hard it is to learn, because you have deadlines for your assignments. You're all taking 4 other courses, so I'm not going to have you writing memory pools and bitwise operations to be as efficient as possible. This is a balance for this course. So what we're going to do is we're going to introduce things, and we're going to make improvements as we go to these systems. Just like we would do in a real game, right? You don't necessarily start off any project by, before it's working, do all the optimization. Like, you don't want to, it's called premature optimization, right? Get it working first, and then hopefully we've architected it in a way such that we can go back and refactor things and make things faster a little bit later. So I want to get you sort of addicted to ECS before you have to spend hours and hours optimizing things. So let's look at a couple of high-level ECS example systems. Now this looks like C++. It's not exactly C++, but the code will not differ much from these examples. So here's a movement system. That's it. It's literally a line of code, right? And again, this should say velocity. I don't know why I don't update that slide. But it basically says, hey, for every entity that exists, take its velocity and add it to its position. That's what it is, right? So if your velocity is, I should be moving to the right by one pixel per frame, then on each frame, you're adding 1 pixel to the position. And so that's the entire movement system. You have updated the position of every single entity with that one movement system. The next one, let's say we have some sort of collision system, right? So some things are going to collide with other things in the game. So in our assignment, one thing that's going to collide is the bullets are going to collide with the enemies. And so we'll show this in the next lecture, how we do something like, hey, give me all the bullets. That's going to be handled by the entity manager. But you can basically say, for every bullet, and then for each bullet, check each enemy. And if our physics system says that the bullet collides with the enemy, take the damage component of the bullet and subtract that from the health of the enemy. And then here, we destroy the bullet. So in this case, what we could do is say, okay, bullets only hit one thing. So as soon as the bullet hits the enemy, it immediately gets destroyed, right? But let's say we pick up some upgrade in the future, because I've played games like this, where you pick up an upgrade where it gives your bullets like a piercing capability or something. So your bullets might be able to go through X number of enemies and survive and then hit the next enemy. Well, we could think of attaching some sort of piercing component to the bullet and say, hey, subtract 1 from the amount of things that it has hit, and if now it's at 0, then we would destroy the bullet, right? So we can have all sorts of interesting gameplay mechanics just by attaching or detaching components. And then the rendering system is kind of equally as simple, and this is a bit of a simplification here. We'll see when we get to the actual assignment. But for every entity, just draw it to the screen. Take the sprite of that entity and draw it at a given position, right? This actually turns out to be like 3 lines of code instead of 1 line of code, but it's still, you get to see this. And one of the really cool things that you get out of this, and I'll talk about this more later when it comes to profiling your code and identifying which parts of your game are slow and fast and which you need to spend time on, because we all want our games to run fast. Because we have all of these different things in all of these different systems, now what we could do is turn them on or off whenever we want. So let's say, okay, I'm not exactly sure how long it takes me to render things to the screen, but if I did turn off the rendering, how fast would it be? Or something that I do in my research, so I do game AI research, and so I've written games that I want to like test new AI systems in, and I want my experiment to run at like 1 trillion frames per second, right? As fast as possible for this experiment so I don't have to wait 2 weeks for it to finish. So something that I can do is turn off the rendering, because I just want this experiment to run and see how the AI did. I'm not watching it in real time, so I can completely just turn off the rendering and let the game go as fast as it wants. So having these systems be compartmentalized like that are really, really cool. Also, it encourages code reuse and like modularity. So for example, I could have someone at my company just spend a bunch of time modifying the isCollision function, right? And then none of the other code in any of the other systems has to be changed because it's just using this modular other system that we used. So the way this is all going to come together, assignment 2 has a different architecture than this because assignment 2 only has one scene and it doesn't change the camera. There's a lot of stuff left out. But once we get into assignment 3 and assignment 4, we'll have the following architecture. So we'll have this class called a game engine. And just because we're using ECS doesn't mean that nothing in our programming uses object-oriented programming. Like, we're still going to have classes, right? Stuff like this. We're still going to use objects. It's not that we're completely throwing object-oriented programming out the window. What we're saying is we're not going to rely on hierarchies and polymorphism to design our entities in our game, right? So we're going to have a class for our game engine. We're going to have a class for a scene. We're going to have functions for these systems, a class for the entity manager. So the game engine will store one or more different scenes. I talked in the past about like Pokemon's a good example where there might be a menu scene, an overworld map scene, a battle scene. And so a scene is typically anything where the logic of the game is different, right? The same controls don't apply to the menu or the inventory screen as they do during the battle screen. Each scene will have its own systems. Some systems may be shared by different scenes, but we'll talk about that when we get to it. And then we'll have an entity manager class, which will use this thing called a factory pattern, where we will actually have the entity have a private constructor. Okay? So you can't actually construct entities in our game unless you go through the entity manager. And I'll talk about all of that in the next lecture, but it's a really cool software pattern that ends up giving us some neat properties in our engine. And entities are going to store components. So components are part of entities. Entities live in the entity manager. Each scene has its own entity manager and systems, and then all of that lives in the game engine. So that's like a high-level overview of a very simple balance between usability and the amount of time it takes us to actually create something like this. So a component, what is it in our course? Well, it's just some data. Now I say it's just data, however, in a couple of our components we have a little bit of logic in the constructor, right? So for example, it turns out, once we get into the collisions and stuff like this, it turns out that when we're using a bunch of rectangles in our game, sometimes it pays to store like the midpoint of something. And so in the constructor, I'm going to take in maybe like the top left position of something, but I'll also compute the middle of it. But what I mean is there's no actual gameplay mechanics going on in the components. So a component class has some intuitive meaning to an entity which contains it. So whenever we name a new class, we typically name it after the gameplay mechanic that we would want to see happen when this happens, right? So something like acceleration, that means something in the game. Gravity, that means something. Health, that means something. So you just don't want to have component 1, component 2. You want to make it descriptive. So how are we going to implement this in C++? Well, first, let's again just reiterate that an entity is an object in the game, right? So something in the game, that is an entity which contains components. So there's no unique functionality on an entity. We don't say like entity.attack, right? Because the entity is literally just stores components. That's all that the entity does in terms of code and in terms of like how we're actually going to implement this. So the entity is essentially a really nice container that stores components in a good way. And something that's very, very, very important is that an entity stores at most one of each component type. So it will never have two healths components. It will never have two position components. But you might say, well, maybe I do want my boss to have two health bars, right? Like some Dark Souls games, the boss has a second health bar. But what you would do there is you would have a health component, and that health component would store both of the healths in it. The important thing is that the container has unique membership for components. It either has 0 or 1 of each of the components that we have in our system. So again, another example would be, oh, but I want the entity to be able to store multiple items, for example. Well, the way you would do that is you'd have one, maybe an inventory or backpack component, and then inside there you'd have a vector of items or something like that. But entities store 0 or 1 of components. That's a good question for an exam, by the way. All right, so components, how components are stored within an entity can be a complex topic. And what we're going to do is I'm going to go over 5 different ways that we could do this. Again, there are like an infinite number of ways that we could do this, but I want to talk about these different ways so you can sort of appreciate the way that we end up landing on the end and why I chose to implement it in that way. So component storage options. One, the first thing we could do is say, okay, since there will be at most one of every component, then I could literally just have my entity class store one variable for each possible component that there could be. Okay, we'll look at that in a second. It has its pros and cons. Or what we could do, and as good computer science students, you probably already realize that this is what we're going to end up doing, is have some sort of collection of components, some sort of data structure that holds all of our components, and then we can use functions like maybe add component, get component, remove component for generality instead of directly accessing the variables within that class. So if we did do the first one, here is sort of how our class would look. And this is by far the simplest way to implement an entity. And you could completely do everything in this assignment and in your own game by having something like this. But it has its drawbacks, it has pros and it has cons. So here, the way we're going to name our components in this class is that the class is going to have a C in front of it, so it'll be a capital C and then transform. So a transform component is the typical name for the component that stores things like position, velocity, acceleration. It's like how the thing is transformed within the game. Transform meaning the mathematical transform, which could be like a translation, a rotation, scaling, all that kind of stuff. So a very basic entity might have a transform, a name, a shape, and a bounding box, right? And then we have like a blank constructor down here that does nothing. One of the interesting things about this, though, is that, as you can notice, well, we can't, at least in C++, dynamically add variables to a class, right? Once I say that this is my entity class, how could I possibly add components or remove components from this? So one of the downsides of a system like this, and we'll see it on this slide, is that our components then would need to have a variable in them to say whether or not it actually has been added, right? So the variables are always going to exist as data in the entity, but whether or not we have said add this component to the entity is a variable that we will need to store. So let's just have a look at that. So here's an example of how we would use this, and it's really simple to use. We would construct an entity somewhere, so this is a blank entity, just call it E, and then I would say e.cTransform equals, and then I just make a new transform class. Maybe that takes in the constructor of a position or something like that. Here I would say the name of this entity is a new C name, and let's call it a red box, and e.cShape is a C shape with some arguments. Now, after I've done that, maybe later I would want to check, hey, does this entity, have I actually given it a name? Have I actually given it a shape, right? So within the component class, we would have a variable, maybe it's called exists, right? So a default constructed component that lives in the entity, like right here, these are all default constructed, all of their exists variables will be set to false. And then whenever we manually construct them, with some arguments, then we set them to true. Okay? And I'll show, I have code I have an example of that later. But then we would say, hey, if the transform exists, do something based on that. Yep.
Couldn't you also store pointers to those types?
Trust me, I'm getting to all of that. Yeah. Any questions? Maybe save it for until I'm done with the component slides, because I'm going through a bunch of different things that we could do. So the benefits are going to be in green, and the detriments are going to be in red. Apologies for colorblind people. A good thing, this is memory safe. It's contiguous memory. There is no heap usage, so it's pretty fast. However, there are some downsides to this. Directly accessing variables is undesirable for many different reasons. One is that it sort of requires knowledge of the internal structure of the entity class. And when it comes to, let me read the other thing first. So I would need to know that there's a variable named this thing. I would need to know that there's another variable named this thing, and that's not great. I don't want to be manually setting this memory all the time. It allows users to directly modify variables, which can be unsafe within some contexts. And the entity contains component check requires another variable. I talked about that. So this exist variable now has to exist. So this is what you're getting at. You know, there's ways that we can do this that don't require this. And this also requires knowing that this variable exists and it has this name. So one of my, I don't have a slide on this, but I probably should, is like one of my #1 rules of programming anything, absolutely anything, especially games, is that at some point you're going to be programming like the game logic, right? And you're like, okay, I'm like up to my neck in details about this game logic of the physics or something like that. The last thing that I want to be able to do, or that I want to have to do, is remember the internal structure of how variables are stored in the entity class. So my rule is, wherever possible, whenever you're having to store or get data, make that as compartmentalized and generic as possible. All I ever want to be doing with the entity class is say, add this component, or get this component, or remove this component. I should never need to know whether that's stored in a variable or a vector or a set or a memory pool or whatever. It's bad to need to know these details because you've got so many different levels in your head already, and one of the most effective ways to be a better programmer is to cut down on the mental load and how many layers of the program you need to have in your head at once, right? I'm sure you've all been programming. You've got like 3 different layers of recursion in your head and someone knocks on the door and it all falls apart like a house of cards and now you've lost 10 minutes, right? You got to get in that zone. So make it as easy as possible to get in that zone by hiding details, and we'll show how we do that in a bit. So to get to your point, which was, couldn't we just do this with pointers? Well, here is the second way we could do this. Again, it's using variables for each of them, but now they're pointers. But they're raw pointers, meaning that it's, and if you watch the C++ video, you know, these raw pointers have a lot of downsides to them. This maybe is how you would do it like 30 years ago. But instead of having an actual stack allocated variable, now we have a pointer to a variable which doesn't exist yet. It's a null pointer, right? So one of the downsides here is that in the destructor of this class, I would need to check all of these things and then free the memory if it has been allocated, right? So memory management is now an issue, which I don't want to have to deal with. But here's how it would look. It would look kind of the same as what we did before, except in order to allocate these classes on the heap, we have to use the new keyword here, right? So that's how we do raw pointer stuff in C++. But the cool thing now is that they don't need to have a variable to say whether or not they exist, because I can just check to see if the pointer is null or not. And one of the shortcut ways of doing that is just to say, hey, if e.c transform. The way that works is I don't need to say if e.c transform not equal to null pointer. You could, there's nothing wrong with that. But what happens is in C and C++, 0 evaluates to false, and anything other than 0 evaluates to true, right? So that's how integers and pointers are converted to Booleans. So here this basically says if e.c transform. Well, this would be false if the pointer was null, right? So that would be false if it didn't have it. If it had any transform, it would not be null pointer, and so this would be evaluate to true. And so that's the way that that would work. So this is good because the contains component check is slightly easier, but that's the only thing that's better about this. Everything else is a lot worse. There's a memory leak here, right? Can anyone tell me what the memory leak might be if I'm not careful? If you can't, it's okay. Yep. Sure, right? So for example, if I've already allocated these things, and then somewhere down here in the code, I say e.cname equals new name blue box, then what's happened? I haven't freed the memory of the previous one, right, of the previous allocation. So anytime I want to change a component, I would have to first check to see if it was null. If it's not null, I would free that component, and then I would create the new one. And that just creates like nightmares all over the place in your code. You never want to have to worry about, like if I'm talking about physics collisions, I don't want to have to be freeing memory, all that kind of nonsense. And so this is very cumbersome and very unsafe. The heap memory usage also makes it slow, right? In the C++ lecture, I showed this diagram of the like 10,000 lines of code that get called when you try and allocate something on the heap. It's crazy. And also it has this direct variable access, which is even way less safe now because it's a pointer. So we could have this point to literally anything in memory, and then we have some, null pointer exception or something when we go to do something else. Okay, so let's take that and modernize it a bit by using smart pointers. Okay, so smart pointers, there are different types of smart pointers. There are unique pointers and there are shared pointers. Shared pointers are a class that implements RAII, which I talked about in the C++ video. So it manages the memory for you. So the good part about this is I no longer have to worry about freeing or allocating things because this class takes care of that under the hood. And it takes care of the quote-unquote garbage collection. It has an internal counter that it uses to see how many references to this thing there are still remaining. And when that counter, in the destructor of this class, when the counter reaches 0, it frees the memory. So that's how it takes care of that. And so this is essentially the same thing that we just did, but it's safer. So we no longer have to use that. However, now it's a bit more verbose, right? We have to use this standard make shared of all of our transforms and stuff, and that's kind of annoying. So it's memory safe. That's good. Shared pointer implements RAII, so that's at least a slight benefit. But the entity contains component check is still easy. Luckily, under the hood, whenever you call a smart pointer like this does the same thing as the raw pointer. It'll check to see if that has actually been allocated. It's slower, much, much slower. Smart pointers have a terribly bad overhead that you want to avoid if at all possible. It is still slow due to the heap memory usage, and it's a larger syntax, and it's a pain to type every time. And again, this is still like, okay, I need to know now that my components are stored as shared pointers, and I need to know the syntax to make shared pointers, and this is just like, please save me from this. I shouldn't have to know all of these details. They should be abstracted away from me. And it still allows direct memory access, which again is bad. Okay, option number 4. Well, let's have a collection of components. We are good little object-oriented programmers, so let's make a base class for a component so we can store all the components in a vector. Okay, that sounds great. What I could do then is I could add a component of a given type with some arguments and get a component of a given type with some arguments. Oh wait, how do I know where these types are in this vector? C++ does not have a great method for reflection like Java has of telling when I'm iterating through this vector, how do I know what type of component this is? Well, the sort of hacky way of doing that is to try and dynamically cast it as the type you want and then check to see if the result is null. C++ is not good at this. So while good in theory, this is actually hard to implement. There's a really cool trick actually that I should have included. It's one of my favorite pieces of code ever where you can call a function with a type name and it'll give you an integer index to pass into this, but it's still slow and annoying. So this ends up being slow in practice due to the implementation details. It's difficult to implement, and essentially what you have to do is you have to take a component-derived class and map it to an integer index inside this class, and it's kind of a nightmare. So we don't want to have to do that. But if we did do that, it would look really nice. We would take an entity, and we would be able to just say, okay, I want to add a transform component, and here are the arguments for that. I want to be able to add a name. Here are the arguments for that. And then if I want to check to see if it has a component, I could say, hey, if e.has ctransform. It's really nice and generic. The person writing this code doesn't know that there's a vector underneath. That could be a map. That could be stored on the cloud somewhere. It could be in a file on your hard drive. It doesn't matter. This is good. This is the good part of this, right? So it abstracts away the storage details of the components, which is exactly what we want, to cut down on that mental load that we need to have whenever we're programming. And it allows storage changes without code changes. So just imagine, we implemented our entire game engine like this, right? And then someone comes along and they're like, oh crap, I just watched Dave's lecture, and it turns out that the reason we're only getting 30 FPS is because we're using shared pointers for all of our variables. How do we change it? Well, now, if I do want to change it, I have to change all of my code in the entire code base that interacts with components, which is basically all of my code, right? So if I store it like this and I use it like this, now whenever I create a component, whenever I reference a component, I have to change all of that code, and it's a nightmare. But here, let's say someone comes along and says, oh, I found a better way than vector to store these things, or we just got some new RAM and here's a special function to optimize it for the PS5 or whatever, right? Now, using this, all those details go away. So the person programming using the entities, they got a 20% speed up and they don't even know how. They're like, okay, that's good. It just sped up overnight. And it's because the people on the back end were doing their job. It is good because the components are stored contiguously in memory, which they were not. Whenever you use pointers, it could be anywhere in the heap. So they're not contiguous, so that's bad for cache. We'll talk about that stuff later. It's the least amount of code to type as well, and so that's really good. However, again, there's this implementation detail of actually knowing where in the vector this thing is. Luckily, C++ to the rescue has a class called a tuple. So tuples are templated. So just like you would have a vector of components, that means that the vector has to store, like it can store as many of them as you have memory for, but it all has to be the same type. In a tuple, typically your use case for a tuple is I'm storing just a few things, but they can be of different types. So that's a really good way to use a tuple. So I'm going to have a standard tuple of my different component types. So C1, C2, these are just like transform, whatever. I just wanted to save space typing. So standard tuple, let's say we have 4 different types of components, C1 through C4, and I'm going to call this variable components. Okay, that makes sense. This is going to be private in my entity class. I am not going to let anyone have direct access to this memory, right? They are going to have to go through the functions that somehow update this tuple. So we're going to have a constructor. We're going to be able to add a particular type of component. We're going to be able to get a particular type of component, check to see if we have the component, and also remove the component if we don't want it there anymore, right? So maybe we have some invincibility frames, so we remove damage or something like that. So this is much faster in practice than the vector-based thing. So even if you do manage to figure out the code for the vector-based solution, this is actually faster because it's all constant time access, C++ behind the hood. The compiler knows exactly where these variables are, etc. All right, so let's have a look. We use it in an identical way to the vector-based solution, which was great because that had the usage properties that we wanted. It abstracts away the storage, allows storage changes without code changes. The tuple uses the stack, but I did look this up. It tries tuple if you have really weird data types in your components that have things like packing of unused bytes and stuff. It can be non-contiguous, but in practice, they're fairly contiguous. It's just that the C++ standard they don't guarantee that they live together in memory, but they typically do. And also, it's like the least amount of code to type, which is nice. So let's have a look at our entity class now. I apologize. Hopefully you can read this. It'll be there in the video and the slides if you can't. But we're going to have our class entity. By default, if we don't type an access specifier, then it's going to be private. So everything above public is private. Everything below public is going to be the public-facing interface for this class. So up here, we have a standard tuple of all our different component types. We call that mComponents. And then down here, we're going to have various functions to get and set those components. However, it turns out that there are a few other things that an entity is going to store other than just the component data. And this helps us with things like managing components. Like, hey, sure, this component has these different types, but I want to be able to tell, for example, is this a bullet? Or is this the player? Or there's two bullets on the screen. Can I tell if they are the same or different bullets? There's a little bit of bookkeeping stuff like that that I also want to store in here. So those things are going to be, from bottom to top, I'm going to say this is an unsigned integer, that's just a size type in C++. I'm going to have an ID, and that ID is going to be equal to 0 by default. By the way, my naming convention here of m underscore means that the variable is a member variable of that class. And that's a really good naming structure because while you are inside a function of that class, you can know whether or not the variable that you're using is a member variable or a local variable just by looking at the name of the variable. And so that's why it's m underscore, because it's a private member variable of that class. So we're going to have an ID. This is just an integer ID. And what we're going to end up doing is that the IDs are just going to be handed out in the order that the entities are created. So the very first entity that's created might get 0, the next one gets 1. By the time a bullet spawns, maybe it's 617. And the way we could check to see, so for example, we may have, in some cases in our game, 2 bullets that are in the exact same position, right? So if we checked all the properties of those bullets, we would say, hey, those are identical. They have all the identical properties. But maybe on the next frame, they're not in the same place anymore. So the way that we can tell if 2 entities are literally the same entity is just to check their IDs. And then you know, okay, these are the same thing. And also, in our collision checking, whenever we loop from, like it's going to be a nested loop, like for every entity, and then you check for every other entity, you want to make sure that you don't check for collisions with themselves, right? Because you don't, if you did, then you would be colliding with yourself every frame, and that would be bad. The next thing is going to be called the tag. And the tag is just a string, and the string is just going to be the type of entity. And this is just for our own sanity. So if you spawn a bullet, give it the name of bullet. If you spawn the player, call it the player. If you spawn a tile that breaks, call it tile that breaks, right? This is just something that we can give it a name for so that we can check these things later. And just as a caveat, this is one of those trade-offs here. If you were making like a super AAA, completely optimized version of this, instead of having a string for the tag, you might have an enum or a bunch of integers that list every possible type of thing in the game. And so like player might have the enum of 17 or something like that. So you would store that there. So ideally, for maximum efficiency, the tag would be an integer, but we're using strings, so we don't need to have everything done in advance. It's a little bit more dynamic. Again, this is one of those trade-offs. So that's what the tag is. And then lastly, we have this alive variable. And alive is initially set to true. And the way we are going to be able to remove entities or destroy entities is all we have to do is set that variable to false. And then on the next frame of the game, the entity manager is going to look through all of our entities and say, anything that's not alive, delete it. And so whenever you go to delete an entity, you don't need to worry about, okay, what type of storage is it using? Do I have to delete it from a map or from a set or from a vector? All of that will be taken care of by the entity manager. So because these are all private variables that we don't want to be modified, we're going to have little helper functions like, for example, is it alive? So when you go to check this entity to see if it's collided with something, well, you can check, hey, is it alive? You may want to destroy it. So this destroy function would just set alive to false, right? And what is the tag? Well, you just have functions for that tag. So yes, even though we said object-oriented design is bad, there's still really nice stuff about object-oriented programming that helps us manage our ECS architecture. Now up here, this standard tuple C1, C2, C3, that gets annoying to type all the time. So what we can do, there's two different ways to give names to custom types in C++. One is called a type def or a type definition, but the more modern syntax is using. So we can say using component tuple equals, and then we're going to have a standard tuple of all the different components we could possibly have in our game. So now, where we used to type standard tuples of all the components, we can just replace that variable name with component tuple. So it's like we didn't have to write a class to wrap around all that. We just say it's a shortcut for naming that thing. Okay? So now we have this component tuple here. All right, Dave, but how does standard tuple work? Is it just magic? Kind of. It is kind of just magic. It's cool. So we declare a tuple with various types. So here, for example, we have a tuple with an int, double, int, float, size t. We're going to call that my tuple. How do I get data from this tuple? Well, there's a couple different ways. One is to just say standard get with the type that we want to retrieve, and then the argument to that function is the variable name. So if I want to get the double from my tuple, I say standard get double from my tuple. And then I can either print that out or I can set it or whatever. So that's the magic access function to this. But look at this, we have two integers. So I cannot say standard get int from this tuple. So if you have multiple of the same type in the tuple, you have to access it by index. And so this acts sort of, it's not a vector at all, but you can access it almost like an array. Whereas if I say standard get 2, then this is 0, 1, 2, so I am modifying this, the third variable here inside the tuple. So that's how I can do that. And I can use that not only to set variables, but this is how I would print the double as well. And you can also use these different types just as arguments to set in the constructor of the tuple itself. So if I had a tuple int string float, call it my tuple, then I can pass in an int, a string, and a float right off the bat to construct this thing if I want to. So luckily, C++ has this really nice data structure. I think this was introduced in C++ 17 that takes care of the implementation details of all of that for us. So that's really cool. So how do we use the tuple within our entity? So let's just have a look back here. We have that tuple there, the component tuple up top. Let's talk about now how we implement all those different functions. And by the way, this is going to be, I'm going to give you the entity class for assignment 2. You don't have to retype all of this, but I want you to understand it. That's the whole point of this course, is to understand things. And if I just gave you the entity class and showed you how to use it, you might not understand how it's working under the hood. So let's have a function called get. The most basic thing we want to be able to do is get a component of a given type. So this is going to return, so this is a template type name t. That's just how we specify generics using templates in C++. And we're going to return a reference to the given type that we care about, and we just use standard get to get that from the components. Why can we do that? Because we have guaranteed that there is going to be at most one of each component type in the tuple by our design. And we also, I'll talk a bit more about const correctness later, we may have some things that aren't allowed to modify this component, and so we would have a const version of that as well. I got to speed up a little bit because I've been waxing a little too long on this. In order to, here's the one bad thing about the tuple architecture, is that we do need to have this exists variable, okay? So that extra variable to see if it's actually been created, we do need to have that. But we abstract that away by having this has function. So we get the thing and then check if it exists. So that's if we know, does this entity have this other thing? Remove is super easy. Remove, we just default construct the thing. So we just blank it. And by blanking it, that exists gets set back to false, and so has will return false when we check has, right? So it's really easy to remove something. Add component, that's the most complex thing. And all of this is just syntax sugar to allow us to forward the arguments of the constructor of the class type we want to add in the function name add. So instead of having to construct the object, the component, and then pass that constructed component into the add function, we can just forward the arguments of the component into the add function. That's what all of this does. So we're going to say get the component, then that component is going to construct that given type and forward the arguments that we passed in. And then we're going to make sure to set exists equal to true. Because if we've added it, it now exists. So that's where we set exists, and then we return that component. So the component default constructor says has to false, and it's only set to true when we specifically add it like this. So that's add. And what we're going to do is we're going to have a different component class for each component we want to implement, and that's the naming convention. So we'll have C transform, C shape, that kind of thing. And components are going to inherit from a base component class which stores any data we want to be common to all components, but it's the most basic type. It's not like complex inheritance. We're basically saying each one of our components needs to have this exists variable, and rather than typing it into each component, we're just going to have that. And it's like zero overhead. We're not talking about virtual functions, virtual constructors, anything like that. It's adding the exist function to or variable to all of our components for us. So exist is whether the entity actually contains the derived component. Default to false, so that default components aren't considered as being as part of the entity. So here's an example component that this is the actual code that we're going to use for assignment 2. We're going to say class C transform, this is a type of component. Everything in our components are pure data and public. So it's going to have a position, it's going to have a velocity. And we're going to have a default constructor for everything. The reason we need a default constructor is because in order to store things in a tuple, it needs to be default constructible. So each of our components are just going to have a default constructor, as well as these sort of convenience constructors where I can pass in, okay, here's the position, here's the velocity, and set those down here. Similarly, we may have a shape. So this would store an actual SFML shape in the shape component. A lifespan might have a total lifespan, a remaining lifespan, whatever, however you want to store that. And then how do we use it? So this might be a system in our game now. So do stuff. We may pass in a vector of entities that we want to be affected inside this function. So for every entity in the vector of entities, do something with it. So I can say e.ctransform.pause. Oh, sorry, this is supposed to say get transform. Yeah, I messed up this slide. But basically, we just take the velocity, add it to the position, and then we set the position of the shape, and then we draw it. Right? So that is how we would actually use this to do things to components. And yeah, I have forgotten to put the get in here, which is a huge oversight. But this might be our entire movement system, right? What is the movement system? For each entity, take its velocity and add it to the position. So this is how powerful this is now, that we can just do like cool systems like this. Some systems only operate on entities which contain certain components. So for example, in order for movement to occur, it needs to have a position, right? So we might want to check if it has a C transform in order to do the movement system. For rendering, it would not only have to have a position, but also a shape, right? Or a texture or a sprite or something like that. For the physics one, we have to check to see if it has a bounding box, because if it doesn't, then we try and get the bounding box and it's just weird data. So we can filter entities before passing them into the system, or we could also just check for entities whether they have the components. So here, for example, here is my lifespan system, and I'm kind of just giving it to you for free here for some reason. So this is the way we're going to use our entity manager. It's just going to have a function that gets us all the entities. For auto, so auto is there, it derives the type from the return type of the function. So you don't need to type entity, you can just say auto. So for each entity, since this is the lifespan system, we're only concerned with updating lifespans here. So if it doesn't have a lifespan, continue, right? I can't work on this thing if it doesn't have a lifespan, because this is the lifespan system. So what I'm going to do is I'm going to say, okay, I've done this one correctly. Get the lifespan component and subtract 1 from the remaining lifespan. Then, if the lifespan is less than or equal to 0, destroy it. That's the whole lifespan system. This just runs every frame, checking every entity for lifespans, subtracts by 1, and then kills it if it's out of time. That's it. That's all we need to do. So anything in your game, like for example, in assignment 3, we're going to be spawning coins. When you hit a block in Mario, it spawns a coin, and it has an animation. Well, we want that coin animation to disappear after a second. Just attach a lifespan, and the systems take care of it. We don't need to check it. We don't need to do anything. We just attach a lifespan to it. Here's another rendering one. If it has a shape and if it has a transform, set the position of the shape and draw it. Super simple. And I've gone back and forth between properly using get and not, so apologies for that. So here is an ECS architecture. That's not exactly what we're doing, but I found it online. I was too lazy to make my own. We have entities that have components, and my system is going to check, does it have the thing? If so, read the thing, update it, and then go to the next system. It's really, really, really simple. Okay, with the few minutes that I have left, I want to really quickly talk about this Vec2 class. So vectors in games, for 2D games, many quantities and properties of these objects have both an x and a y vector, or a coordinate, and these form a 2D vector. So it's not a vector in terms of like a C++ storage vector, it's a mathematical positional vector. So for example, we might have a position that has an x and y, and a velocity that has an x and y, and we don't want to store x's and y's separately everywhere, and so we're going to make a 2D vector class, and we're going to call it Vec2. Some notes. I'll go into more details about this in a later lecture, but I'm going to first just show you the programming architecture and why we're using it, and then we'll use it later. And just keep in mind that SFML already has a version of this thing that we're going to make, but we want to do this, get our hands dirty from the ground up and really see what's on the go when it comes to this, how we make it and how we use it. So whenever we make a new class, the architecture decisions that we have to make are what do we want to store? Right? So whenever you talk about something, whenever you have a noun, that's a variable. Whenever you have a verb, that's a function, basically. So the things we want to store are the x and y coordinate. The things that we want to do with those x and y coordinates, those will be functions or operators on that class. So possible operators, we may want to add vectors, subtract them, multiply, take the length of them, normalize them, rotate them, whatever. So we're going to come up with something that looks sort of like this, where we have a class Vec2, and we're not going to have getter and setter functions for our x's and y's in these, because when you have a game that just constantly on almost every line of code is modifying and reading x and y values, just make them public. And we're going to say pos.x rather than saying .getX.set. Oh my God, it's so annoying. So sometimes, yes, you just do want the variables exposed, and this is one of those. We'll have a constructor, and we'll have some operators on those. And I'll do some live coding as an example for this. So I'm going to skip this, so I have 10 minutes left to do this little bit of live coding, because I think that it's a little bit more engaging. So I have just some notes on the top. What I've done here is I've made a new class and just given it a couple of very, very basic things. So my class here is going to have a float x and a float y. And by default, if this is default constructed, we want to give these values of 0. If I had just said float x and float y without saying equals 0, then the default constructor in C++ doesn't give them any values. So it would just be like whatever happens to be in RAM at that point. So that's bad. So you can give them default values up here. Then I make a constructor which takes in a float and then sets the internal variable. So that's all very basic. And the only other thing I've added so far is a print function so that I can actually just print out the x and y. So if I come down here to main, let's say I go, okay, I'm going to have vec2, v1, and this is going to be 100, 100. And down here, I'm going to have vec2, v2, and this is going to be 1,000 and 1,000. All right. Then let's just say I'm going to v1.print. And then I'll compile and run that. Hopefully it works. Okay, so good. My live coding hasn't been a disaster so far. So let's say, all right, what are some things that I would want to be able to do with these vectors in my game? Well, probably the most basic thing is add two vectors together, right? So, okay, one way I can do that, and I'll show you a couple different things, is I could have a function called add, and this is going to be a function, so I'm going to say v1.add v2. Since it's void, it's going to add in place. So it's going to take v2 and add it to v1. So I'm going to want to have nice const correctness. So this is going to take in a vec2 reference, and the convention here, RHS means right-hand side. So whenever you have an operator, it's going to take a right-hand, no, that's, I'll just call this v. And so now I won't talk about that here. So this would just be, okay, how do I write this function? X plus equals v.x, and y plus equals v dot y. All right, basic stuff. Come down here. And now I'm going to say, before I print it out, I'm going to say v1.add v2. What should be printed out? Someone who's paying attention? Yeah, 1100, 1100. Hopefully, there we go. All right. Now, but how do I add two vectors not in place? Maybe I want to have a new variable. Like I want to just like int a equals 7 plus 3. I want to be able to do that. Okay, so if I want to be able to do vec2 v3 equals v1 plus v2, I'll come down here and I'll delete this. Oh, invalid operands to binary expression, vec2 and vec2. So no plus operator exists. The compiler doesn't know how to deal with this. So we can add any sort of operators we want to our class, which is a really cool thing about C++. So what's the return type of this? Well, it's going to return a new vec2, right? And this is an operator, and this operator is plus. And here we're going to pass in a const vec2 v, and down here we are going to return a new vec2 where the x is what? What's the x here? I know it's late. All right, x plus v dot x. So what should y be? Y plus v dot y. All right, so I'm taking the x, adding it to the other x, the y, adding it to the other y, and returning a new vec2. So now, why did it print that? Because I wasn't printing out vec3, right? I was still printing out vec1. So let's go down here. v3. There we go. So now we have a new variable, and wherever I want now, I can just plus things. That's pretty awesome. I could also do minus, right? I won't do that because that's just a waste of time. You could also do minus here. Let's do another thing. Let's say I want to have an operator here like multiply. Well, multiply might only take in a float, right? Let's say I want to take a vec2, multiply it by 3. Okay, so let's say I have vec2 operator star, and this is going to take in a float f, and now I'm going to return a new vec2. That's going to be x times f, y times f, right? So this is going to scale this vector. So now I can multiply vectors. So now, okay, vec3 equals v3 times 5. Okay, anyone good at math can tell me what's going to print? There we go, right? So now you can see, okay, I'm going to add all these different things to my vector. I'm going to have equals operators to tell if they're equal. I would check x and y, etc. I could write a function in here, which is the length. So this might be float length. And this would return like the square root, the Pythagorean theorem, right? So you'd have from 0, 0 to this, what's the length of that vector? That might be cool. You could normalize a vector. We'll talk about that later, where you keep it pointing in the same direction, but it has length 1. All sorts of different stuff. Yep.
Can you do, with the way you have it implemented now, can you do v3 times equals 3, or do you have to implement times equals on its own?
I'm not sure. Let's try it out, because we could very easily do times equals, but v3 times equals, because you'd think that it would know to do that. Yeah, so no viable overload for this. We would have to implement operator times equals, and that would be easy enough. All right. The last thing I want to show is this concept called chaining, which is pretty interesting. So up here, I have add. Now let's add another thing called void mult. So mult is going to do the same thing that our other one did, but it's going to do it in place, right? So it's going to be mult is going to take x times equals f and y times equals f. So down here now, I can say, instead of doing what we just did, I'm going to say v1 dot add v2 and then v1 dot mult 5. That should probably give us the same answer that we had before. And then v1.print. Yeah, so that can do that. But this can be a little verbose sometimes when you want to be able to do multiple things on the same line. So what we can do up here, these are void. But a cool trick is that I could return something from here. And what I could return is a reference to a vector. But what vector do I want a reference to? Myself. So whenever I call this function, the return type of that function is a reference to myself. I'm going to do it down here as well. And this is a pointer to this object, and so we dereference this to get the reference. Now down here what I can do is pretty neat. v1.add v2. What does that return now? It returns a reference back to v1. So if I were to put parentheses around this, the return type of that is actually v1. Right? So that is a vector, or a vec2. So let's just delete that because I don't actually need them. That was just for illustrative purposes. But what I can do now is, because this gives me a vector, I can do this. So I add it, then multiply it. And this will just work. We can just do it all on the same line. And then after that, if I wanted, oops, to add v2 again, I can do that. Oh, I got something wrong here. Oh yeah. How did that happen? Must have hit some copy and paste hotkey or something. .mult.add. There we go. So it's kind of neat. You can implement these formulas on one line like you would with binary operators, but with in-place operators. And I know some people who swear by this stuff because it's like add it, then multiply it, then do this. It's like a cool one-liner. And I know some people who absolutely hate it, and they'd bash you on the head if they ever saw you using it. But I just think it's a really cool thing that you can do with these operators and functions when it comes to stuff like this.